Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. NASA EscaPADE, Mars Atmospheric Escape Mission. NASA's EscaPADE mission, scheduled to launch in the spring of 2025, is a twin spacecraft initiative designed to investigate the processes behind the loss of Mars' atmosphere. This mission seeks to provide quantitative measurements of how charged particles are stripped away from the Martian upper atmosphere by interactions with the solar wind, a phenomenon that has played a crucial role in Mars' climatic evolution. The spacecraft will focus on directly measuring ion flows, electron distributions, and magnetic field variations in the regions where the solar wind meets the upper layers of the Martian atmosphere, thereby offering detailed insights into the mechanisms driving atmospheric escape. Mars' atmosphere has undergone significant changes over billions of years. Today, it is a thin layer composed mainly of carbon dioxide, with surface pressure averaging about 610 pascals, less than 1% of Earth's atmospheric pressure. This sparse atmosphere results in a cold, arid environment where liquid water cannot persist on the surface. In contrast, ancient Mars is believed to have had a much denser atmosphere, rich in carbon dioxide, which created a greenhouse effect, warming the planet and allowing liquid water to flow. Evidence supporting this includes geological features resembling river valleys and lake beds, as well as recent findings of ancient beaches, suggesting the presence of large bodies of water approximately 3.5 to 4 billion years ago. The transformation from a warm, wet climate to the current cold, dry state is attributed primarily to the loss of Mars' magnetic field around 4 billion years ago. Without this protective shield, the atmosphere was exposed to solar wind and radiation, which stripped away much of the atmospheric gases into space. NASA's MAVEN mission has provided data indicating that a significant portion of the Martian atmosphere was lost through this process, fundamentally altering the planet's climate and surface conditions. The EscaPADE mission's primary objective is to quantify the rate at which Mars loses its atmosphere and to identify the dominant processes responsible for this escape. By deploying two nearly identical spacecraft in complementary orbits around Mars, EscaPADE will be able to capture spatial and temporal variations in the plasma environment. This dual configuration is essential for distinguishing between localized phenomena and global trends, ensuring that the measurements provide a comprehensive picture of the dynamic interactions between the solar wind and Mars' atmosphere. Each spacecraft is equipped with advanced instruments such as ion and electron analyzers, magnetometers, and plasma wave sensors. These tools are optimized to detect even subtle changes in particle densities and energies, which are critical for accurately determining the rate of atmospheric loss. Extensive ground-based testing and simulations have been conducted to validate the performance of the spacecraft and their scientific instruments under conditions that mimic the harsh environment of interplanetary space and the Martian upper atmosphere. The mission's design leverages decades of experience from previous Mars explorations, ensuring that the spacecraft are robust enough to endure extreme temperature fluctuations, radiation, and the vacuum of space while still delivering high-resolution scientific data. The flight trajectories have been carefully planned to maximize the opportunities for in situ measurements, with both spacecraft scheduled to enter their respective orbits at altitudes that allow them to sample a wide range of atmospheric conditions around Mars. The data acquired by the EscaPADE mission will play a pivotal role in enhancing our understanding of how Mars transitioned from a planet that might once have supported a thicker, more habitable atmosphere to the cold, arid world it is today. By precisely measuring the energy and density of escaping atmospheric particles, the mission will help scientists build more accurate models of atmospheric evolution. These models are not only significant for understanding Mars itself but also have broader implications for planetary science, as they provide a basis for comparison with atmospheric processes on other terrestrial bodies, including exoplanets. The insights gained could refine our theories regarding planetary habitability and the long-term evolution of planetary environments in our solar system and beyond. The operational framework for EscaPADE is designed to ensure that the twin spacecraft can effectively relay large volumes of data back to Earth, where the information will be analyzed in real time and over extended periods. Advanced communication systems have been integrated into the spacecraft, enabling continuous monitoring of their health and performance as well as the integrity of the scientific data collected. In addition to real-time data transmission, the mission plan includes robust contingency protocols designed to address potential anomalies during the journey. This meticulous preparation reflects the mission team's commitment to achieving high-precision measurements, even in the face of the inherent challenges of interplanetary exploration. The engineering behind the EscaPADE mission represents a significant advancement in spacecraft design and instrumentation. The integration of sensitive plasma instruments with resilient spacecraft systems exemplifies the progress made in adapting complex technology to the unpredictable environment of space. The mission's twin spacecraft not only complement each other scientifically but also serve as a redundant system, ensuring that even if one instrument or component underperforms, the other can still provide valuable data. This approach maximizes the scientific return while mitigating risks, an essential consideration for any deep space mission. In a broader context, the EscaPADE mission is a critical component of NASA's ongoing efforts to explore Mars and understand its past, present, and future. By focusing on the fundamental process of atmospheric escape, the mission addresses a key question in planetary science. How do interactions with the solar wind contribute to the long-term evolution of a planet's atmosphere? The answers provided by EscaPADE are expected to refine our understanding of Mars' transformation over billions of years, offering empirical evidence that can be compared with theoretical models of atmospheric loss. Such comparisons are vital for validating our scientific hypotheses about the history of Mars and for planning future missions that may one day explore the possibility of past or present life on the red planet. In summary, NASA's EscaPADE mission, launching in spring 2025, is a focused scientific endeavor aimed at quantifying the escape of Mars' atmosphere through precise, in situ measurements of plasma interactions. The twin spacecraft, equipped with state-of-the-art sensors, will provide critical data on how the solar wind interacts with the Martian atmosphere, thereby shedding light on the processes that have shaped the planet's evolution. Through rigorous testing, advanced instrumentation, and carefully planned orbits, the mission promises to deliver a new level of detail regarding the dynamic and complex nature of atmospheric escape. The results of EscaPADE will not only enhance our understanding of Mars but also contribute valuable insights to the broader field of planetary science, influencing how we perceive atmospheric evolution on both nearby and distant worlds.